Whether it's in a biological system or in a beaker in the lab, it's often important for us to be able to control the pH of a reaction as it's occurring in order to get the desired result. The way we do that is with buffers. Looking at just some physiological pHs, oftentimes people will refer to physiological pH. Well, there are a lot of physiological pHs. It really depends where in the body you are. So in the stomach with gastric acids, the pH can be really quite low, right down around pH of 1. And as we go through a number of different fluids, different compartments of the body, we see that the pH can vary quite a bit, all the way up to pancreatic secretions, where it's up around 8.1. So it goes from being very acidic to being notably basic. One other thing, just to reinforce and note here, neutral pH at body temperature is 6.8. So remember, when we're not at 25 degrees Celsius, our idea of neutral, it still means that the H3O and H3O plus and OH minus concentrations are the same, but the actual pH that we measure at that neutral condition is slightly different at different temperatures. So what is a buffer? How do we maintain all of these different pHs in different compartments of the body? So a buffer is, and there are two important things here. Number one, a buffer is a solution that resists change in pH when small amounts of acid or base are added. That's sort of the functional part of what a buffer is. The second point here is a little bit more descriptive of what a buffer is. A buffer is an approximately equimolar mixture of a weak conjugate acid, weak conjugate base pair. So if we think about that in equation terms, here I've got a Ka type equilibrium equation written out where I've got a conjugate acid and its conjugate base. And if we think about a buffer, if we make up an approximately equimolar mixture of a weak conjugate acid, weak conjugate base pair, if I set up my system so that I've got a whole bunch of HA and a similar whole bunch of A minus present in my system, we can kind of think about that as, as a little bit of a balance here. So I've got a great big concentration, relatively speaking, of HA, of the weak conjugate acid, and a similar large concentration of the weak conjugate base. If I add just a tiny little bit to either side of this, it's not going to send the balance flopping wildly one way or another. It's going to adjust a little bit. And in fact, if we think about it in terms of this equilibrium chemical equation, if we think about it in terms of Le Chatelier's principle, if I add a little bit of acid, what's going to happen? I'm going to add a little bit of acid and it's going to adjust. The equilibrium is going to shift towards reactants. So if I add a little bit of acid, it's going to react with a little bit of that weak conjugate base and form the weak conjugate acid. Similarly, in the other direction, if I add a little bit of base, it's going to react with the weak conjugate acid and shift that over to the weak conjugate base. So it's really a balancing act between the two that relies on there being a relatively large amount of these two chemical species present in order to absorb those small amounts of acid or base. When we're talking about buffers, it's important for us to really specify what we mean by a good or an effective buffer. So in order for a buffer to be effective, the pH of our buffer should be within, and probably has to be within, about 1 pKa unit of the pKa of the weak conjugate base. So if I've got a pKa of 9 for my weak conjugate acid, then I can use that system as a buffer from about 8 to about 10, so within about 1 unit of the pKa of the weak conjugate acid. Also, the conjugate acid concentration and the conjugate base concentration should each be at least about 100 times the Ka of the weak conjugate acid. And that really is getting to our, the size of our boxes here. We need enough of both of these present so that we can absorb a little bit of a shift without wildly swinging back and forth. A couple other important points here. When we refer to a buffer concentration, what we're typically referring to is the concentration of the conjugate acid plus the concentration of the conjugate base. So the total concentration of these two put together. We also will talk about buffer capacity, and I've actually mentioned that a few times, so let's formally define it. Buffer capacity is the amount of H plus or OH minus that a buffer can absorb before the changes start to be too extreme. When we're thinking about buffers, there are a few pretty important buffers. Biological systems, these are relevant, as well as just being able to cover a wide range of pHs. So the carbonic acid carbonate buffer system, we've got actually two different buffers here. Carbonic acid bicarbonate is one buffer system, and that has a pKa of pKa of 6.4, which means that it can be a buffer somewhere just below neutral. So about 5.5 to about 7.5, we can effectively buffer things with that carbonate buffer, with that carbonic acid buffer. If we look at the second deprotonation, if we look at bicarbonate to carbonate, that has a pKa of 10.3. So now with this sort of the same system, we can buffer up from about 9.5 to about 11.5 with that buffer. Another one that comes up very often, and this is carbonate, is one that's important in the body, specifically in the blood and a few other places. Another one that's important definitely important in the laboratory setting, is the phosphoric acid system. And the reason this is a really handy one is because it's got 3 different levels of buffer systems. So we can deprotonate 3 times, and that can buffer at pH 2, pH 7, and pH 12. So it really gives us a nice broad window of pHs we can buffer in using some sort of a phosphate-based buffer system. And finally, an acetate-based buffer system. This is also a pretty handy one. Right around pH 5 provides a good buffer, lets us go into that little bit acidic, but not wildly acidic side of the pH scale. There are a lot of things we could talk about with buffers. I don't think we need to necessarily go into quite the math detail that we might otherwise go into. The important thing is just to remember, buffers are systems of a weak conjugate acid, weak conjugate base pair that control large changes in pH when small amounts of acid or base are added. Be sure to read over this section in the textbook, look through some of those examples, and I will see you next time.